Okay. Hello, everyone. I'm Alex. This, as Tobias said, is the start of Compiler Social, so I'm going to be a lot less formal. And we are going to stay with equality saturation because it's apparently a hot topic these days. But we are going to go to a completely different part of, program execution stack. And if before we heard about equality saturation for essentially synthesizing hardware, I'm going to talk about how you do it at a very top level of a machine learning compiler stack. This is a joint work with a bunch of people. In particular, there's Leo, who I saw somewhere, who is from Oxford, of all places. Why do you come from Oxford to Cambridge? And Jakub Bakursky, who is a local, and who, for the joke, we've been on this project for a year. It's the first time I see him for real life. I love modernity. You can do research with people and never see him. Okay. I don't have two subtalks here, but my very wordy title has at least two parts of it. The first is equality saturation, and I knew that there would be a talk before me, so I didn't waste any efforts presenting what equality saturation is. Now you're all experts in it. It's like you use rewrite rules to saturate graphs, and you kind of add more nodes into a graph until you cannot add anymore. So it's saturate. And I guess just to add to a very similar picture that you've seen before, why it's slightly different, you'll see. Why this is important for compilers specifically is sometimes in a compiler you can do a rewrite that prevents you from doing any further rewrite. So here's a slightly different example where I have an A divided by 2 and multiplied by 2, or vice versa, it doesn't really matter. And normally, if you multiply something by a number and divide something by a number, it should cancel out. You just get back your original operand. But people and compilers are smart. They think, if instead of dividing by 2, I could just do a right shift. And the right shift, at least on integers, you can do it. It's much faster than division. So how about I replace the division with a shift? Sounds great, you optimize something, but then by doing that, you prevented the possibility to cancel out that division by 2, multiplication by 2, because now you have a right shift followed by a multiplication, and you kind of need to reverse and understand that, that thing before was a division, so you can actually apply the second right and cancel out. And that's what eGraphs give you by preserving the information that you had before. Now you know that in the eGraph, your rewrite of replacing division with right shift is actually in the same equivalence class. And you can still apply that transformation back and get, in my example on the left, to equivalence between the outer division and the A node. So you can actually have rewrites that are not destructive. And that's a very powerful property when you're trying to apply that in a compiler setting. Okay, that's all you need to know about equality saturation, I think, or everything that has not been said yet. And my job is done here. Thank you very much.
That was my question. It was about this, the destructive rewrites that you want to avoid.
Okay, perfect. It was entirely planned. We knew you were going to ask that question. And the second part is real-world machine learning compiler, and what that even means. And some people who know me, or I've been presented as somebody who worked on MLIR, so you might expect that the real-world machine learning compiler is MLIR, and if you expect that, you would be wrong. Because I have another talk called MLIR is not an ML compiler, and it's really not. What is an ML compiler, however, is a project called OpenXLA, and it's a project that's used by TensorFlow and JAX, one of the big production compiler infrastructures. It is also available inside PyTorch. Google really pushes for that being in PyTorch, but it's not the same by default. It is based on MLIR. It is also based on LLVM, has been based for a while, so it's kind of very connected to the general LLVM MLIR crowd. And it's a compiler, and structured as a compiler, so normally it has a pass pipeline. It's a rather long pass pipeline, boring, but basically, you take your tensor graph representation in some form, you apply your algebraic simplification rules, x minus x is 0. When you do machine learning, you don't care that much about correctness, so, you divide by 0, okay, let's assume that's also 0, nonce never happen, ints never happen. If they happen, if your machine learning still generates plausible text, it's fine. So okay, let's do some more aggressive simplifications. Then we do a transformation called loop fusion that's really powerful. Then, we do some simplification again because why not? And then we do layout assignments and buffer assignment and more. And like, wait, did I just say we do algebraic simplify twice? Well, actually, not only twice. I think it's done at least a dozen times in many places. And it gets obnoxious in that pass pipeline. And what happens is this kind of changes people make into the XLA compiler. Oh, it was doing a transformation. It was moving an operation called reshape before an operation called dynamic slice updates. Detail doesn't matter, but basically it was moving something and making things work or worse. So it was bad, performance was bad, let's not do that. But what happened after, like shortly after, I have dates here, I think. Yeah, like a couple of months after, is, well, now that we don't do it, something else is broken. So we need to add yet another copy of this algebraic simplifier and it gets out of control. Like, do we have to run it after every pass? And that's, if you worked on compilers before, that's bread and butter of like compiler writers. It's tweaking around pass pipelines. And basically the question we asked ourselves at some point, can we do better than this phase ordering essentially? And I hear cool people are all doing equality saturation now. So how about we try that? And yeah, I heard lots of opposition to that, especially saying, you're going to build this huge data structure, and then you need to do this extraction procedure. It's kind of very complex. And you know what? I have another commit from XLA that says, well, the algebraic simplification pass in some cases was exponentially complex and was fixed. I'm sure it still is. What's worse, I know it's not a fixed point algorithm. So a non-fixed point algorithm was exponentially complex. And there's more. So we solve complex problems in compilers all the time. It's not a problem to try with equality saturation. There are more challenges. So the representation it works on is not an E-graph. It was never meant to be an E-graph. So we'll see how we can do that. And the other thing is traditionally E-graphs were applied to more low-level stuff like arithmetic rewrites, hardware as you've seen. Maybe slightly above, there are some papers trying to apply it to tensor algebra, but not that many. And what's more, it's unclear if it will scale to large machine learning models. So we set off to kind of do that. It's a social. I'm not sure the food arrived. I had like a note on the slide of saying like, hold my beer and wanted to actually have a beer. But yeah, it's kind of hold my beer kind of paper where people were not convinced it's possible, and I'm going to show this. So XLA works on a representation called stable HLO. HLO stands for high-level optimizer, but basically you can think of it as a roughly 100 of operations on tensors. Many of them like element-wise addition. You probably know about them, like half of them are that. They're like matrix multiplications, tensor products, convolutions, usual suspects you would see in a machine learning workload. It's a spec. So all the semantics are clearly defined, and it's easy to create more or less reasonable rewrite rules on those. And then it comes in the form of the MLR dialect. So it is a static single assignment form operating on immutable tensors, also great for rewriting. It comes with a declarative specification in a format called TableGen. I, like anybody in LLVM community, like to hate on TableGen. But a very good thing about it, it's declarative and it's really easy to kind of parse and analyze. So if you want to parse a definition and produce something based on it, it's great. What's more, you can define rewrite patterns directly in that format. And that's what we work with. So just to give you an example that I took from, if I remember correctly, it was a Llama 2. So it's an example where we do some computation, we do dot general, it's a matrix multiplication in this case. We do multiply it with a constant, it's kind of stupid, multiply with -1. We do exponent, add, divide, multiplication, another thing. If you've seen this before, yeah, have an example where it says it's a sigmoid linear unit. And this, well, that's a normal SSA. If you've worked with compilers before, you are not very surprised. If you haven't, well, this percentage thing is a value. It's only assigned once. You can use it multiple times, but you cannot ever reassign it. It simplifies analysis. And basically, that is kind of your E-graph or initial form or the E-graph in the inverse. So here we start with the first operation saying it's general, and if you want a E-graph form of that, it gets to the very bottom. Because in an E-graph, your E-node or E-class will have as operands E-classes of everything we had in the operand. So we get the same format inverted, and we can say, well, we are having a multiplication that takes as operand a result of dot general and a result of division, which takes as operand an add and a constant, which takes. So it is a rather straightforward encoding of this thing in an E-graph. What's here, I took that example on purpose. It's actually written that way in the code, but multiplying with -1 is kind of inefficient. When you have a negation operation, even on floating points, you can just go and swap your sign bit. So we can then turn this in the E-class of multiplication into an E-class containing two nodes. Multiplication is -1 and negation, and then we will go and figure out that it might be a better version of the same program. Okay, the encoding itself looks relatively reasonable. The difficult part is how do we tackle that at scale, because, well, I showed this before, this part with like 7 instructions is this tiny unit there that is part of a feed-forward network, that itself it's part of a decoder layer, out of which we have probably like 32 at least in a moderately scaled model. So all of this will get replicated many, many times. So if you want to just take your entire model and throw it to an E-graph, that just takes a lot of memory. If you try to saturate it, well, most of the time you will not even achieve saturation. You will not, in a reasonable time, find like all possible combinations. So we need to do something about it, and what people would normally think about is, no, we need to split it into subproblems. We all followed, simple basic computer science class, divide and conquer. So that's exactly what we do here. We take that big problem and we split it into chunks. And initially, we thought we could be smart and look at this as, okay, it's a graph. We can do some sort of max flow, min flow properties, strongly connected components, whatnot. And guess what? It was not working out really well when we tried to run it. And our hypothesis, more or less, is it is ignoring information about temporal proximity of things, because normally all things, they come from a program that's written by people. And what they tend to do is they tend to write programs that use data close to each other. So if you use something, it's likely that you are going to use it again. Or if you're using it again, it's likely that you are going to use it in a shorter period of time. That's basically why we have caches. That's, again, a relatively well-known fact. So a rather naive application of splitting. So instead of saying, oh, these two are not connected in a data flow way, we're going to say things that are connected syntactically in a program should go into a separate independent E-graph. Syntactically means they're just close or next to each other. And that works surprisingly better than anything we've seen so far based on any sort of data flow or max flow analysis on the SSA graph. That's a bit surprising, but it works. And what it gives us as a possibility is to limit the size of E-graphs from a bigger model. So we can then do equality iteration on a smaller graph. We can do it for a subgraph in a model. We can do it for multiple simultaneously, but they don't grow as much.
Sorry.
Yep.
As in producer consumer or program order?
Program order.
Okay.
Yes, that is surprising.
Okay.
But again, if you look, it's unlikely. Like if you take an unrolled model, it's very unlikely your consumer is very far away from your producer.
Right, but if you take two loops and you take the window in between the two, then...
I'll get to loops. Loops are a bit tricky in this representation. That's the other trick we have to play, but basically we want to separate them along really syntactic program order. Okay, the other thing is, well, in stable HLO there's like kind of 100 operations, and I can imagine several thousands of rewrite rules, and this will be really big. And then loops, yes, there are loops. Loops are kind of annoying. The good thing about stable HL, there is only one kind of loop. It's called a while loop. It's almost never used. So how about we just completely ignore its existence? Which is also what we do. Well, for loops, we leverage a particular aspect of MLR design where complex operations like loops use a feature called regions. And regions are sort of small subprograms that you put inside an operation. And then we can treat each region as a definitely separate subgraph. We can further subdivide it if we want. And then the loop itself, well, we don't really care about that loop. It's loop that is, in any case, we don't have any good rewrites for it. So we do that for loops and some other kinds of operations, because out of many operations, we know that some of them we have meaningful rewrites for. So like typically you have macmodes, you have convolutions, those you want to optimize. You have your poor exponentiation somewhere, it appears every once in a while, not so much. So we kind of black out and black box a certain class of operations we don't have good optimizations for. And since this is an SSA form operating on immutable tensors, that's not a big deal. It means, okay, we have to black out something that might be a separation point, but I know that data is coming from something. It's as if it was a function argument. So there is no nasty side effect thing going behind, which lets us completely ignore parts of the problem and say, okay, my data arrives. It arrived to me, it will not change behind my back, nothing bad will happen while I'm in this controlled environment. With these two tricks, we're actually able to run and sometimes saturate graphs on, well, most of the time, saturate graphs. Sometimes you have to cancel out on timeout. We are able to run this, and we are able to run this early in the pass pipeline. And that's another thing we wanted to do. We wanted to inject this into a pass pipeline because we've seen work before which takes, okay, let's take a tensor program, let's throw out the XLA compiler, and let's just generate LLVM or assembly. Sounds good, doesn't work. Or, well, it does work, but it takes really a lot of time, and the generated programs are really, really suboptimal because you kind of mix together optimizations at a very high level where you reason about tensors with optimizations at a very, very low level where you reason about individual values or like small vectors. However, being inside a pass pipeline creates another problem for us. And another problem is, okay, if you run this very early, then the compiler can come and, as usually compiler passes do, undo some of the optimizations. We spend so much time trying to figure out what to do. So it doesn't necessarily fully undo, but there are things that have a tremendous effect on the resulting performance. In particular, these three that I put on the slide on purpose and highlighted, which are fusion, layout, and buffer assignment. In particular, like, who here does not know about fusion? I think everybody does, right? Okay, great. Fusion can influence performance, and what's tricky is we can affect the way the fusion heuristic in XLA is structured by, even mutating the syntactic order of programs, of statements in the input. How do we model that? For that, I need to go a tiny bit into egraph extraction, as was also mentioned before, and there are actually many ways of extracting from an egraph, but first, what is extraction? Given this form, basically when you have an E-class, to get from an egraph to a concrete program, all of them do the same thing, all of them are equivalent. You need to, inside each E-class, pick a node inside that equivalence class that you'll use. So you can basically say, out of these two, because I have a very simple example, I need to pick either one or another. And it's a decision problem. So let me introduce a decision variable. Finally, in probably 10 years, I get to use some Mason slides. I'm pretty happy about that. So I get to introduce a decision variable. And then we in compilers tend to like ILP for no reason, but decision variables are binary variables. You can put it into an integer linear program. And then we have algorithms to find an optimal solution of an integer linear program. It's an NP complete problem, but at least you have a provable solution, you have good implementation. However, the problem with that would be that your optimization objective, or a cost function, should be linear. It should be expressible in an ILP. And that the naive implementation of that just means that, each of these nodes have a certain cost. So multiplication will have a cost of 4 and negation will have a cost of 1. So if I just add up the cost of everything I've chosen, I get a good number. Sounds good, does not work very well in case of fusion. For example, if you have a matrix multiplication followed by a dozen of linear operations, which in this case you do, maybe not a dozen, but a lot, those might get fused into a multiplication. So a lot of your cost that actually comes from data motion goes away after you apply fusion. And that is not modeled in this naive function. So what we did is we modified, at least for this approach, the objective function or multiple functions in the ILP formulation. So first we want to take into account fusion, where if we have two nodes that will instantiate, we will have an extra Boolean variable that says it will be 1 if both A and B are extracted and they are theoretically fusible. So there is nothing that prevents us from fusion. And we will multiply that with some fusion bonus. We extract that from the XLA cost model, which itself looks at the amount of data that's being moved for this operation from slower memory to faster memory. So typically that's what you achieve by fusion. And then we want to maximize that. So we want to maximize the amount of savings we get thanks to fusion. And another observation we've made is for the two other parts that I will not go into much detail, but basically if you reason about these things, data layout are important. I guess, people seem to be old enough to know the difference between C and Fortran arrays, like row major, column major. Yes, and you know it matters, right? And it matters even more when you have multidimensional tensors, and matters even more when your compiler decides, okay, my program is a convolutional network. I happen to have a very efficient convolution for that particular part, but it is only efficient if your data is in a particular order. So you have like NCHW and you run on NVIDIA GPU, so you have that library that's like 10 times more efficient than everything you have ever seen. But I absolutely must have that order, and I have to propagate it all the way. That's what XLA does. So we need to just be aware of that, and we make a simplifying or simplistic assumption that if the layout and buffer assignment is absolutely perfect, there will be no copies. And what we observed is if something has no copies, meaning it's like no data transfers that are spurious. So what we observed that if there is one use of that, one use of a tensor, it is very likely that we will get it, well, it's almost certain that we'll get it the right layout, because it's one use, so we can propagate through one uses down the SSA representation. We can always propagate up, because in SSA there's always one definition. So it will propagate the correct layout, and we will never have to inject a transpose, which is a costly operation that would induce a copy. And we are trying to minimize the number of operations that will have many uses. With that two modifications of the cost functions, well, we are able to run this. We are able to run this on a bunch of programs. As you probably guessed, I'm mostly interested in optimizing for the ML space, so other people are not. So we took mostly ML, but also some scientific compute. We ran it through a quality situation, which is a weird Franken monster of egg, other project, MLIR, a thing called enzyme XLA that has little to do with XLA and little to do with enzyme, which is automatic differentiation. What's important from there is we took 3 sets of rewrite rules, one from a previous paper called Tensat, one from a project called Enzyme XLA. The details of that project are irrelevant even to the name. What's important is that project looked at XLA and realized that XLA is not doing a bunch of algebraic rewrites or even XLA-specific rewrites. For example, if you take a slice of a tensor that was produced by a padding operation, and your entire slice happens to be the value that you were padding with, like how about you don't produce a new tensor that's bigger only to take a part that you know is 0 because you're padding with zeros? Like that transformation was not happening. And there's like several hundreds of those that, as I said before, are expressed declaratively, which makes it easy to bring into a different system and define the same sort of rewrites on e-graphs extracted from stable HLA, and then we added, usual arithmetic or algebraic rules about associativity and commutativity. Again, ML, so correctness, fast math is good enough. We ran that on a bunch of GPUs and one CPU, and yes, the results may not look super impressive if you just squinted it from last, but one of the cases that I want to highlight here is, there are two versions. One is just the Llama 3. That's the one I wrote by hand by reading the paper, and I wrote it in a very naive way, and not running our tool and running just a set of the same rewrites in a fixed point fashion gives us a 20% speed up. We cannot extract anything good from that graph because I am presumably a bad programmer. However, if you take the same model from MaxText, which is a production implementation of the same model by Google, suddenly if you just apply the same set of rewrites under a fixed point, you get 10% worse performance. Now, if you apply this set of rewrites with equality saturation and those cost functions, you get a 15-ish% improvement. Same rewrites, different approach. And that's exactly the kind of problem I was showing before with like right shift, but at a bigger scale. On a slightly newer or slightly older, and bigger GPU, we have similar-ish results where we can sometimes find better programs than a fixed point, and sometimes worse. And when it's worse, it's usually because it doesn't saturate. And finally, if you run that on CPU, that looks more impressive because presumably nobody just optimizes machine learning programs for CPUs these days. Also, maybe the kind of rewrites we apply is not ideal for this optimization. So we took rewrites that we saw were necessary, but they were not necessarily the most impactful ones. What's also interesting is this notion of segmentation into subgraphs and variation. So what happens here, we took two examples and we ran it on CPUs because it was faster to run. But there is a sort of sweet spot on the size of the segment, which here is around 50 instructions per segment, where we get to roughly as good total speed up as possible at the lowest possible optimization time. We have a more like an explanation of a more negative example where basically it fails to saturate. So at some point, it's not even fails to saturate. At some point, the ILP extraction will time out. And that's where we are currently looking at, and I hear people look on equality saturation. So I like ILPs. My PhD was on polyhedral. That's kind of all ILPs, but I feel kind of limited. So I'm really looking for a better way of extracting from this equality saturated graph to get a good machine learning program. That's all I have. Thank you.
Yeah, thank you so much. So we have time for some questions.
Just a silly question out of curiosity. You mentioned the timeout, and again, last slide.
Yeah.
Have you looked at things like frontier effects, like things like if I wait like fractions of a second before timing out, I get a much better solution, or do you find like empirically so far that the best transformations to saturate are explored earlier in your?
So it's an ILP. Yeah, I don't think we tried to look at how ILP performs over time.
Yeah.
It might be a good idea, but basically we generally think that there are two hypotheses we have. One is we don't have good enough rewrites, or we're not controlling the right things. Like ideally, I would control fusion in ILP directly.
Yeah.
That's also an ILP thing. And the second is the cost model. The cost model is still, we are limited by it being linear, and it's really not. Right. So these are what our current working hypothesis, but yes, like we can try and see performance over time.
Just out of curiosity, you are looking
Yeah,
to...
we have not. It's a good idea. Thank you.
Cheers.
You mentioned the syntactic splitting in the beginning, and I think you said that like it sort of may be intuitive because when you write a program, some related parts are next to each other. Did you find that this varies depending on the framework that you use? Because I guess, for example, JAX, I think, emits all the constants at the very beginning. So is there like a difference in whether you can make the assumption depending on the way the framework emits the stable HLO?
So we have not looked in this project, but I have seen that before. And what usually happens is we don't look at stable HLOs directly emitted by the framework. It gets pre-processed after that, and then typically gets like through canonicalization and common subexpression elimination and all sorts of things that tend to bring these things together, even if they weren't.
Thanks.
Hey Alex, thanks for the talk. If you wind up embedding things like fusion decisions into the ILP, do you eventually rediscover Pluto? Like what? Like where do you end between like doing full polyhedral?
Yeah, I think we can eventually get to that, but basically these fusion decisions, like this fusion is a producer-consumer fusion. Pluto fusion is a loop fusion. So they're not exactly the same. You can extract both, and like doing producer-consumer fusion itself is an ILP is feasible. Adding a quality saturation to that is fun. Well, I do not hire a PhD student, unfortunately, but if somebody wants to do that, be my guest.
Over here. Hey, so one question, so depending on if you're doing prefill or decode, so there is either compute or memory pressure. So this kind of distinction, sort of, is it possible to reflect it in the cost function when you're doing selection in the compiler?
Good question. I think, well, it's just a decision, so it is possible to reflect that, but you somehow need to communicate that from the program. And then...
So you haven't looked into that. And can I ask a second one, follow-up? Okay.
Good for me.
For the graphs, just to get an idea on the sort of quality of these rewrites, do you have a baseline where you run, say, Lamo on PyTorch, Triton backend, or
so it's related to how JAX does it. So 0 is JAX, and this is above, below what JAX does.
I see. Okay, so no other framework. Cool. Thank you.
Yeah, we don't have other frameworks because, like, even if you compare JAX to PyTorch on the same model, you'll see a difference. And then when we were doing this, it was still impossible to properly connect XLA to PyTorch anyway. So doing different framework, different compiler, you know, your comparison gets really unsound.
So good that you're on this slide. I would have thought optimization time should be monotonic in segment size. That's the idea, right?
So I could not...
So on the right, the larger the segment size, the longer it takes to optimize. But on the left, that's not happening?
Oh yeah, that's where it... So on the left, the optimization times goes up.
It goes down and then it goes up again.
Yep. So I do not think it should be monotonic in the end. We're solving an ILP in this. And
I see. Okay, so the ILP difficulty.
Yeah, and the bigger it gets, it might get into a longer, like less happy case.
Yeah. Okay, so my real question is something like this. I love equality saturation, but I've never understood why the word saturation is there, right? Because you're going to run out of memory. So what you've done is, sliced it up so that you don't run out of memory. But then you said, we don't get the right answer because we don't achieve full saturation.
Yes.
But presumably you meant full saturation in the particular segment that you heuristically chose.
Yes, or all segments. Yes, we never, like in any case, it is already partitioned, and within we lost information by partitioning. But even within a segment, you might not saturate, or we have multiple segments, then you might not saturate some of them.
Yeah, and so I guess I'm saying maybe the segmentation should just be considered one of many strategies in not doing saturation, in judiciously expanding the E-graph.
Sounds like a good idea. Do you want to do a PhD with us?
Do you remember the numbers of kind of nodes, right? Like how big does it get? How small does it?
I don't, but I have people who do. You can meet them at the social.
And another question of so there's another paper doing something similar that complained about circular kind of paths in the graph being particularly annoying to extract. So I'm just wondering whether you also ended up with
So there is a trick in the ILP encoding that lets you handle that. Like I didn't want to put it on the slide because it's a lot of math, but there is a trick in ILP that says I'm only going to extract a certain number of steps in a cycle.
Okay, excellent. So I suggest we slowly move towards the compiler social part. So step number 1 is to thank Alex again. Thank you so much for this.